Welcome back. Now, when we talk about the force of gravity, then there are also other simplifications that we have made. For example, we assumed that the center of gravity of the Earth is located in the center of the Earth. That's a good enough assumption for statics and dynamics, but it's not the real truth. And that's because if the Earth was a perfect sphere with constant density, then indeed the center of gravity would be the center of the sphere. But in reality, you have certain areas inside the Earth that are more dense than other regions inside the Earth. You can see that here, for example, you have more density. Your density is higher here and here as well compared to the other regions. And then maybe you have some kind of very dense area here and then here. So you can see that these areas here, they have higher density. And so because of that, your mass distribution is not equal inside this sphere. And because of that, the center of gravity is not exactly in the center of the sphere. It's shifted. Maybe instead of being here, maybe it's slightly shifted here or maybe a bit here. And so in reality, it matters where you are on the sphere. However, as mentioned before, our assumption of a perfect sphere with constant density is good enough for statics and dynamics. Nevertheless, if you end up designing orbits for satellites at advanced level, then you will have to deal with varying densities inside the Earth. But as I said before, for statics and dynamics problems, it doesn't matter. And that's because for everyday life, these kind of irregularities are very small. These are the things that space engineers need to worry about. Then we are also neglecting the force of gravity from other objects, such as the sun or the moon. When you do your statics or dynamics problems, then in reality, not only the Earth applies force of gravity to you, but also the moon and the sun. But compared to the Earth, their effects are negligible. So again, unless you are a space engineer, this is something that you don't have to take into account. Then another simplification is that we are assuming that the Earth is not rotating. Remember when I said that in the Newtonian mechanics, you assume a non-accelerating reference frame. However, when something rotates, then that is also acceleration, because rotation means that your velocity vector has changed its direction. Maybe the magnitude of the velocity vector stays the same, but when its direction changes, then there is still a change in the components of those vectors. For example, here we can say that Vx equals 5 meters per second, but then Vy equals 0 meters per second. If we assume that this is x and this is y, then this velocity vector does not have a component in the y direction. But now the velocity vector has an angle of 30 degrees here. The magnitude is still 5 meters per second, just like it was here, 5 meters per second, but now your Vx, it's 5 times cosine 30 degrees meters per second, and Vy, that's 5 times sine 30 degrees meters per second. So the velocity vector components have changed. And that's why there is acceleration even when a body rotates. And so when you have another object here, object A, and when you measure this force of gravity that the Earth exerts on object A, which is this one here, and it points to the origin of the center, then the Earth obviously rotates around an axis, let's assume that it rotates about this z-axis. However, it rotates too slowly to play a role in statics and dynamics problems. In dynamics, I will also cover rotating frames. I will teach you how to deal with them. But in statics, you don't have to worry about it. I'm listing these assumptions because I want you to be aware of them. Finally, I also want you to be aware of the rigid body and concentrated force assumption. So for rigid body, let's assume that you have a beam and you have a box here on top of this beam. In reality, this beam will slightly bend. But this bending is so tiny that in statics and dynamics, we assume that it does not bend at all. In other words, we assume that objects do not deform. That's rigid body assumption. And now, for concentrated force, let's assume that we have a car. You obviously have force of gravity that pulls it down, and because of that, there are normal forces applied to the wheels of the car. In reality, the wheel touches the ground something like this, and so you have distributed load here. But assuming that the wheel is pressurized well enough, then for the purposes of statics and dynamics, we will assume that this normal force acts on a single point on the wheel. This idealization is called the concentrated force assumption. We will be applying this assumption whenever this force distribution is very tiny compared to the rest of the environment that is being analyzed. And now, let's practice some unit conversions in the next video, and then we will be ready to start learning the main course concepts through problem solving. Thank you very much. Welcome back. So let's now practice some unit conversions. First of all, let's get familiar with the SI units a bit more. You are already familiar with the units of length, time, mass, force, and moment. They were meters, seconds, kilograms, Newton, and Newton meters. So these are the SI units. The units meter, second, and then kilogram, they were your fundamental units, which means that other units like Newton and Newton meter, they can be written in terms of meters, seconds, and kilograms. However, what if what you're measuring is too big or too small for these units? What if the length of something, let's say the distance between two planets, is 1 billion meters? Would you write it like this? Or what if the gravity force between two small particles is 0.000000009 newtons? You can see that our units are not very suitable for these kind of numbers. Therefore, to make them more suitable, you have something called prefixes in the SI unit system. For example, let's take the force unit Newton. If this is your force, then you can also write it like this. Fg equals 9 times 10 to the power of minus 9 newtons. Or you can write Fg equals 9 small n and then big N, which is newtons. But what's this small n? This symbol n, it stands for nano, and it's one of the prefixes used in the SI unit system. So you would say that the force of gravity is 9 nanonewtons. Then if this is your distance between two planets, 1 billion meters, then you can also write it like this. D equals 1 times 10 to the power of 9. And then that would be meters. Or you can write D equals 1 big G and then meters. This symbol G, it stands for giga, and it's another prefix that is used in the SI unit system. So you would say that the distance is 1 gigameter. So when you have an exponential form 10 to the power of minus 9, you can simply replace it with nano, and people will know that it's something times 10 to the power of minus 9. Similarly, when you have an exponential form 10 to the power of 9, then you can simply replace it with giga, and people will know that it's something times 10 to the power of 9. And so here you have the most common SI prefixes. 10 to the power of 9, that's called giga, and this is the symbol. Then 10 to the power of 6, that's called mega, and the symbol is this. So now you know that when someone tells you that I can store 300 megabytes of information on my pen drive, then now you know that it's 300 times 10 to the power of 6 bytes of information that this person can store on that pen drive. This 10 to the power of 6, that's your mega. Then 10 to the power of 3, that's kilo, and the symbol is small k. Then 10 to the power of minus 3, that's milli, and the symbol is m. 10 to the power of minus 6, that's micro, and the symbol is mu. And finally, 10 to the power of minus 9, that's nano, and the symbol is small n. They are used because that way it's more convenient to express very big or small quantities. If something lasts for a very short time, let's say that it lasts for 5.75 times 10 to the power of minus 6 seconds, then you can simply say that it lasts for 5.75 microseconds. You will simply use this prefix here. So you have base units like meter, seconds, Newton, and then you can simply combine them with these prefixes here. For example, you can say that something is 2 kilometers long, or something happens for 7 nanoseconds, or the force is 10 millinewtons, or something is 15 millimeters long, or maybe the force is 17 micronewtons, or maybe it's 17 meganewtons, or maybe it's 17 giganewtons. So all these prefixes here that you can see, they all tell you what powers you're dealing here with. 2 kilometers, it means 2 times 10 to the power of 3 meters. 7 nanoseconds, it means 7 times 10 to the power of minus 9 seconds. 17 giganewtons means that you have 17 times 10 to the power of 9 newtons. Now there is one exception though, and the exception is mass, kilograms. The base unit for mass is kilograms, but you can see that it already has a prefix. You have K here. That's kilo. So in reality, the base unit should be gram or G. So this G is gram, and then you could combine it with kilogram or megagram or gigagram or milligram, microgram, nanogram. So I've listed them all here. Nanogram, microgram, milligram, kilogram, megagram, and gigagram. And of course, according to that, you might think that this gram should be equivalent to meters and seconds and Newton However, because of the fact that 1 gram is such a tiny mass for everyday life, there is an exception here. And the exception is that the kilogram is made to be a base unit that is equivalent to meters, seconds, Newton. And by equivalent, I mean that usually it's kilogram that is used with meters and seconds and newtons and not gram. So if I say that the mass of something is 1,000 kilograms, then you can also say that it's 1 times 10 to the power of 3 kilograms, or 1 times 10 to the power of 3, then this kilo here, that's also 10 to the power of 3, and then you have grams here, so essentially you have 1 times 10 to the power of 6 grams, or 1 megagram. So I just want you to know that even though kilogram is a base unit here that is usually used with meters and seconds and Newton, if you do something like this, like something is 1,000 kilograms, and then if you rewrite it like this, 1 kilogram, that would be totally wrong. You might think that, okay, since kilogram is the base unit, then since kilo is 10 to the power of 3, then 1,000 kilograms should be 1 kilograms, but it's wrong. The kilogram already contains a prefix, which is this one here, that's your kilo, but because of the fact that for everyday life, kilogram is a lot more suitable than a gram, because of that, this kilogram is often used with meters and seconds and newtons. Because meters, seconds, and newtons, they are also very suitable for everyday life. The only difference is that meter, second, and Newton, the units that are most suitable for everyday life, they don't contain any prefixes, but the unit for mass that is most suitable for everyday life, it does contain a prefix, which is kilo. So that's the exception.